Hi everyone, my name is Hans Banerjee, and today I'll be talking about nanotechnology and its uses in silicon photovoltaic cells. And a lot of people nowadays are talking about the silicon and its various limitations and it not being so-called good enough for solar cells anymore. Well, today I'm here to tell you that silicon is not dead, and there are these various processes involving nanotechnology and on a nanoscale that improve the silicon cell. And I'll be talking about two processes in particular. One which covers stuff that happens on the inside of the cell, and one that covers stuff that happens on the outside of the cell. Okay? But first of all, I'm just going to tell you for a bit why I am talking about solar cells. Okay? After all, everything in this class has been on devices and transistors and so on and so forth. We haven't talked much about power, so why would I talk about solar cells? Well, you see, the answer is pretty simple. So basically, the solar cells are very similar to LEDs, which we will talk about in week 10. The top diagram is a diagram of an LED, which basically shows a voltage source and a p-n junction, and electrons and holes being excited across the junction, and photons being emitted when they recombine. Okay? In a solar cell, it's the exact opposite. Photons come into the p-n junction, and then electron-hole pairs are created. They drift across the junction, and then they recombine, and that's how you get current through your solar cell. Okay? So basically, as you see from these two diagrams, the solar cell is just a reverse of an LED. So if we're talking about how nanotechnology can help LEDs in week 10, why can't we talk about how it helps solar cells? And that's what I'm here to do. Okay? So, that's why I'm talking about solar cells. So now I'm going to talk about what makes a good solar cell. Okay? So, on the left is a graph of a solar cell current versus voltage curve, or IV curve. And basically, it looks like a diode curve just flipped over, which makes sense because I just explained the similarities to LEDs. Okay? So, the maximum power you can get out of a solar cell is equal to the area of this dark pink rectangle. And the dark pink rectangle represents the maximum power point of both voltage and current. And you want the biggest area of the dark pink rectangle possible. Okay? So, this is given by the equation power equals current times voltage times the fill factor. Okay? So, you'd want to increase all three of those things. However, currently the best way to maximize efficiency in silicon cells is to increase the short circuit current, or just the current in general. And the reason why is the voltage is essentially fixed, okay? As you know from basic electronics classes, the turn-on voltage of a silicon diode at room temperature is roughly 0.7 volts, okay? And you can't change that essentially unless you change the material, okay? But if we're stuck with silicon, we're stuck with the VOC being stuck around 0.07 volts, okay? Furthermore, the fill factor is nearing its ideal state, okay? People are getting really good at eliminating parasitic resistances from the cell, which are the main limitations on a fill factor. And so they're getting really good at making contacts, they're getting really good at the process technology and avoiding contaminations, and yeah. Basically, the fill factor is nearing its ideality. So basically, the only way to go is to increase the current, okay? So maximizing current, you can do it in two ways. One is preventing surface reflections, which allow more light to get into the cell and increase the current that way. And we'll talk about that a little later. But we can also prevent premature recombination of charge carriers, okay? And premature recombination just means electron-hole pairs recombining before they reach your device, which is bad because that's just a waste of a photon that was used to excite that electron-hole pair in the first place. Okay? Now, a measure of this is called quantum efficiency. Quantum efficiency is just effective carriers divided by total carriers. And this is a function of wavelength for two reasons. One, because of the solar spectrum, and the amount of total carriers is different at each wavelength. And two, the certain cells absorb different wavelengths better than others and make more effective carriers at certain wavelengths. So the effective quantum efficiency will never be greater than 1, obviously. You can't have more effective carriers than total carriers. But we want to make it as close to 1 as possible through all the major wavelengths of the solar spectrum. Okay? So that's what makes a good cell. Alright, so now how do you make a good cell, and how do you achieve this good quantum efficiency and this good current, okay? So this is a method I worked with at the University of Texas with Dr. Sanjay Banerjee, who has no relation to me, by the way. It's just have the same last name. But it's called plasma-enhanced chemical vapor deposition, okay? And basically, this system deposits N-type, P-type, or intrinsic silicon via the addition of gaseous silane, diborane, or phosphane to the chamber. And basically, these things are just added to the vacuum chamber, and some heat's thrown in, some plasma's thrown in, and basically, at the end of it all, silicon, doped or undoped, depending on what you put in there, comes out, okay? Now, the pros of this method, okay? It occurs at low temperatures. And low temperatures are great because they cause minimal damage to the silicon lattice. And you don't want the damaged lattice because the damaged lattice means those damaged lattice sites act as recombination centers, which ruins your quantum efficiency. Okay? Furthermore, there's a low risk of contamination in the gases being used. They're all really pure and really filtered. And there's a low risk of contamination versus like liquid dopants or solids. And that's also really good because contamination leads to more recombination sites, okay? But there is no free lunch in the semiconductor industry, as they say. And there are some cons to this method. It is slow. It only deposits a few tens of nanometers per hour. And furthermore, it produces amorphous silicon, not crystalline silicon, okay? It usually deposits amorphous silicon, which has a lower mobility than crystalline silicon. So it's in general not desirable for semiconductor applications. However, in this application, it's not too bad, as you'll see in the next slide. Because there's these new types of cells called heterojunctions. And a heterojunction is just a fancy word for saying an interface between two semiconductors of different band gaps, okay? Like amorphous silicon and crystalline silicon. And a diagram of a heterojunction cell is shown here on the right, okay? Okay? Now, why would a heterojunction cell be better than a normal cell with just crystalline silicon, or what we call a homojunction cell, okay? And the heterojunction turns out to have higher efficiency in testing than homojunction due to passivation. And passivation, I'm going to explain it really quick, involves mitigating these dangling bonds of the surface of the silicon, as shown in the bottom right. And these dangling bonds are not good, because at the beginning, at the surface, lattice sites are unbound, and these unbound lattice sites act as recombination centers, which damages your quantum efficiency, as I've said many times before, okay? But in the heterojunction cell, it is passivated, okay? These bonds are tied up by this amorphous silicon hydride, and basically these bonds are tied up with hydrogen bonds, and that makes them not act as recombination centers anymore. So this helps passivate the cell, okay? Furthermore, the thin P layer, which occurs because the process is so slow, is actually good because it reduces fruit surface recombination and helps blue response. Because blue photons are absorbed very close to the surface, and so therefore the closer the p-n junction is to the surface and the thinner your p layer is, the better blue photons will be absorbed. And that improves your quantum efficiency at blue wavelength, at short wavelengths, okay? And finally, you can do a dual heterojunction cell. You can passivate both the front and the rear with amorphous silicon, and that reduces surface recombination in both surfaces, which further improves the cell current. Okay? So this graph shows what I'm talking about. Basically, the blue graph has no intrinsic amorphous silicon hydride layer. So because the cell is overall thinner and the p-n junction is closer to the surface, the quantum efficiency is higher at blue wavelengths. Okay? But when you add in the amorphous silicon, intrinsic silicon layer, or the I layer as they call it, your current actually increases. And the reason why is the passivation is better with this amorphous intrinsic silicon layer. And that allows carriers generated further in the cell to more efficiently come out of the cell and become effective carriers. Okay? So basically this I layer helps the current, and therefore affects the cell, increases the cell efficiency. So most cells do include this I layer nowadays. Okay. So now we're going to turn from the inside to the outside and talk about texturing of silicon solar cells. Okay. So on the left and the right are two SEM images, and they're basically two common patterns that are used on the surface of silicon cells. This one's called the random pyramid pattern. This one is called the random pyramid pattern, and this one is called the inverted pyramid pattern. But the question is, we've been talking all about like planarization and chemical mechanical polishing and all. Why would we want the surface of a solar cell to be textured and rough? And the answer is, well, we like texture because it traps more light in the cell, basically. If you have a flat silicon substrate, light comes in and then some light is reflected straight back out through Fresnel reflection. And let's just say that's R, okay? The proportion of light reflected out is R. R is some number between 0 and 1, okay? Well, if you have a textured silicon substrate, the light can strike the surface multiple times, as seen in this diagram. And whereas you're losing R with a flat substrate, you might only lose R squared, which is smaller than R, because R is between 0 and 1. So you'll lose less light to flat out reflection, okay? Furthermore, the light that comes in is refracted, okay, at an angle. And that's good also, because it increases the path length of the light in the silicon cell, rather than it just coming straight in and straight back out, like in a flat cell. Okay. And if the path length is longer, that just means the photon has more time in the cell to be absorbed and create an electron hole pair, which is good, right? Furthermore, if you put in a textured rear reflector, it's makes things even nicer, because then the light bounces around and does all these crazy things due to total internal reflection, and the path length increases exponentially over just a plain flat cell. So, and therefore the time for a photon to excite an electron hole pair is much, much greater if you have this textured cell. So that's why we like texture. Furthermore, we can do a textureception, as I like to call it, and put textures upon textures. Okay? And basically, some group in Taiwan has done this. They have made these big pyramids using a basic etch, but then they put these small grains on the pyramids, as you see in diagram C. Okay? They put these small grains on the pyramids themselves, and they call the big pyramids "big" in quotation marks because they're only a few microns in size. But they call the big pyramids macro texture, and the small grains on the pyramids nanotexture. And they claim this nanotexturing has greater effect on the good properties of texturing than just the big pyramids alone. And they did a study to show that it does indeed help. Like this etched nanotexture actually significantly reduces reflection, especially at shorter or blue wavelengths, and that it actually does help trap the light better, which leads to the increased quantum efficiency at almost all wavelengths. So the answer is that this nanotexturing done through the acidic etching has actually helped over just the normal basic etched big pyramids. Okay? So that's how it helps. Okay? Now we can go one step further and combine the two. Okay? We can combine the heterojunction cell with the textured cell and get a textured heterojunction cell. And it makes this really crazy looking diagram here on the left side. Okay? But you can see it's just the diagram from a few panels ago with some jagged lines. Okay? And these types of cells, although they are hard to make at the moment, have led to the highest efficiencies for silicon cells to date. Okay, the leader by far is Sanyo. Okay, in Japan, which has achieved an efficiency of 23%, which is 3 to 4 times higher than a commercial silicon cell. Okay, and that is a big improvement in efficiency, even though they're just using the same materials. And they're, of course, doing some proprietary stuff that we don't know about to increase the cell efficiency. But it's easy to see that heterojunctions and texturing are definitely helping the efficiency of the cell. Okay? So thank you for watching my video, and I hope I have shown you a little bit about how nanotechnology and nanoscale processes help solar cells. And I hope I have convinced you that silicon solar cells still have viability, especially with the help of nanotechnology.